So hi everybody, it's good to see you all back to our Shitlux series. So today we're going to have the very talented Dr. Sara Campbell. So Sara is a quantum engineer, I would call her. And when she was doing her PhD thesis, she helped build one of the most precise clocks that exist on Earth, which was very cool. But now she works in industry. She works for a company called Honeywell, and she is developing quantum computers there. So uh, she's going to talk a little bit about her present favorite qubits, trapped ions. So it's super cool to have you here, Sara. Thank you for being here.
Great, yeah, thanks Clarice, and thanks yeah, everyone for showing up. Ooh, let's see if I can figure out how to share my screen. Where's the button? On the video thing? No. Video settings. Haha. Now let's see how long it takes an experimentalist to figure out how to use a computer. Nah.
So, oh, maybe you don't have assigned co-host. Sorry, I think you didn't have the.
Oh, here we go.
Okay, can you try? Oh, okay.
Yeah. Share screen.
And Sara, can we interrupt you and ask questions?
Oh yeah, please do.
Cool.
Unless you're a professor, then nah. I'm just kidding. No, you can interrupt me. It's fine. Slideshow. Great. Let me just hide this. All right. Can everybody see that? Okay.
Yeah, that's good.
Great. Can you see my mouse?
Yeah.
Nice. Great. Yeah. So hi, I'm Sara Campbell. Yeah, I'm a physicist at Honeywell Quantum Solutions, where we make quantum computers based on trapped ions. So I was told to give a bit of a science discussion first, and then talk about my general career path. Yeah, I saw there's a number of professors in the meeting. Like, I hope you just came for some like Katy Perry animations or whatever. It's not a very technical talk, but yeah. So just as an introduction, I was a huge fan of Richard Feynman, always, and like. So he was trying to explain something to a friend, right, at this one time, and like he was like, "Oh, I can explain that. I'll prepare a freshman lecture on it." And then, even Richard Feynman, pretty smart guy, came back and he's like, "Nah, I couldn't reduce it to a freshman level. That's because we really don't understand it." So, if anything's like confusing or whatever, I think it's probably my fault. Don't feel bad or whatever. Yeah, so I think you already saw some introduction lectures, but yeah, we do computing with these quantum bits, and like I feel like they're not that weird. It's kind of just like a coin rotating in the air that just hasn't like landed yet. And I feel like when we as humans try to look at it at the end of the day and get a measurement, that process causes the coin to like have to choose a side. And so I think you've seen this. Where did my mouse go? Ooh, pointers. Fake laser. Okay, so I think you've seen this picture before, where you can sort of understand how these, the two bits, the 0 and the 1, are represented. It's a sort of a point on this sphere, where kind of the South Pole is one state, the North Pole is the other state, and the interesting thing is there can be like a phase also between the two states. And so basically, how much it's pointing to the 0 or the 1 state is sort of like you have a weighted coin or something. So it's like how much of the coin is heads and how much of it is tails, and then it's just like rotating around kind of in a circle, and then how it lands, sometimes how it lands depends on where it was in this rotation. And so that's not super weird, the fact that like you have these two different states, they have different energies, typically. Not that weird that the phase between them, that they would have a phase between them and it would change over time. Like if you think about a sound wave or something, say like a higher frequency, with same amplitude or whatever, you know, I'm vibrating these air molecules or whatever like that much faster when I'm singing a higher pitch. And yeah, you can see over time these two you know, high energy and low energy kind of waves, you know, their relative phase is going to change, and that's because they have different energies. And so what do we use for our qubits at Honeywell? We use ytterbium atoms, and atoms are cool. And then you can like remove one of their electrons, and then they become an ion. So we have a ytterbium plus. It's kind of nice when stuff's charged. You can sort of like move it around more easily. And the cool thing about atoms or ions or, you know, these building blocks of nature is that each one of them is fundamentally identical. They're not fabricated. You know, it's not this chunk of stuff that I have to make. Like nature provides us with these identical qubits. And so we have these two different energy levels in these ions, which I think you already heard about from Clarice's lecture. And so I can give it some energy and you know, use that to change the state, because there's an energy difference.
Sarah,
yeah.
There's a question in the chat, and people feel free to speak up. There's a question: why ytterbium?
Why ytterbium? That's a good question. I think so. Ytterbium is one of the weird ones, but it basically acts a lot like the second column in the periodic table. So that's like the ones with 2 outer electrons, and then we ionize it, and then it only has 1 outer electron. And I think one of the answers is that we're kind of bad at controlling stuff that doesn't essentially look like hydrogen. So like that first column of the periodic table, there's 1 outer electron, and you can kind of ignore the rest. And yeah, it's easy to talk to with lasers. I think that would probably be my answer to that. And it has these 2 nice qubit levels where, like, you know, you want your 0 and your 1 to be something that can live for a long time. Like if you know, the 1 would spontaneously change to the 0 all the time, like you're you know, not gonna have a great computer if you're just like randomly flipping bits. So yeah, that's a great question. And so yeah, we use lasers, and like, you know, the errors, like the things that affect the computer are like really fundamentally understood. Like we completely understand them. I think what we don't understand is like at any given moment, like what, you know, what's what's causing the problem right now? Because unfortunately, you know, we take these perfect qubits and then we put them in our you know, man-made environments. And so I think that the challenge is to be able to actually control them. And so yeah, these qubits, you know, after they're ionized, then they have charge, and then we can just control them with just electrostatics, like electric fields. We also have a radio frequency field that helps provide the trap that helps hold them. And so yeah, the chip looks basically like this. That's an actual photo. Whoops. And yeah, you can see in here, those little stripy guys, those are actually the electrodes, and the ions sit somewhere like here. And we put some radio frequency down these 2 rails right there to also help hold them in space. And so the ions, they kind of just hover right above this surface. And we do our stuff.
How do you put the atoms in there?
Yeah, they just like fly in. Actually from the bottom. We have a hole. Can you see it? I don't think so, but there's a tiny hole, like basically here. And then yeah, there's a chunk of ytterbium, and we heat it up to like 500 degrees Celsius. So it's moving, I don't know, 500 meters per second, pretty fast, I think. And it's like flying through, and then we just you know, capture it. We have to ionize the atom, so it's like flying in from the bottom. Yeah, we ionize it, we cool it down really fast, and then we hold it in here. Yeah, so if you zoom in on this little square, this is kind of what it looks like. yeah, so it flies in, and yeah, we hold it in this this little, so you can kind of think of like you know, what we're doing to this charged thing with all of our fields is, it's kind of like just making a little cup that we hold the ion in, and then we can move our little cup around, which is nice. So with these electrodes, we just change you know, the voltages on the electrodes, and we can just move the ions around. And we have these, like, you know, gate zones where we have our lasers aligned to. So if I want to change this guy from yeah, a 1 to some superposition between 0 and 1, I just shine a laser on it. And, you know, sort of at the heart of computing, right, is you have these inputs, you have like zeros and ones, right? And you have to sort of connect them together and get an output that depends on the input. Like, that's what happens when you add two numbers. You have, you know, these lists of digits, right? And then like your answer depends on what you put in. And you kind of have to like do the same thing every time, the same operations, but depending on what inputs you put in, you get a different answer. So like, you know, one classical gate is like, you know, an AND gate or whatever, or maybe you're writing a little Python script and you have this AND thing, and like, so if you have, you know, a 1 and a 1, you know, you get a 1 out. So yeah, we need to be able to make our qubits talk to each other. So we can have them all separate, and then we merge them together just using our electrodes. And yeah, then we shine the lasers on. And so when the ions are like sitting together and they're trapped, so whoa, I didn't realize this had some sweet music. So yeah, when they're sitting together in the trap, you know, they're both charged, so they both experience Coulomb repulsion. And so, you know, their motion in the trap becomes coupled, and they have these different modes where they can oscillate. And that's kind of fun. And then yeah, as you add more and more ions, you know, that you can have all these different modes that happen when they're all talking to each other in the trap. And you can see like this one, you know, this center of mass mode, for example, it's going pretty slow where they're all moving together, and then like these are going faster, etc. So all these different modes have different energies, and you know, a laser has an energy. The photons of a laser has a particular energy, and so using the laser, we can actually just talk to all these different modes. And this is sort of the way that you can get the ions to talk to each other, so that you know, you can do a gate where, depending on you know, the spin of the ion, or like, you know, which state it's in, and depending on the motional modes, the laser will talk to it in different ways. And so that's how you can like get an output that depends on your inputs. And so we call it a little dance. Like, that's actually what we call it in the lab. I don't know if everyone does that. Can I go to my next slide? Come on, computer. Here we go. Okay, yeah, so the dance is kind of like this, right? You have like this technical manager who had to review my slides said like, I don't know, man, like Katy Perry, maybe like the kids listen to something else these days. So anyway, I'm old, but so say you've left shark and right shark. Say when they're pointing up, right? I think it takes energy to stand on your head. So I'm gonna say when they're like this is the 0 state. And so this is like essentially the gate we do. You always have the same, you know, Katy Perry on controlling the dance. She's represents the laser, and yeah, depending on the what you put in, you get all these different outputs. So you get this like superposition where like you get these different phases between the two superposition states. And the interesting thing is, like, you know, when it's like when you get the state like this, this is sort of what you call entangled. So you know, both sharks can be either up or down, but like every time left shark is up, like right shark is also up, and like every time left shark's down, right shark will also be down. Versus these guys, they're opposite, and these guys, they're always together. And so like, yes, this sort of aspect to quantum computers like is sort of one reason, at least, they're good for doing some things that a classical computer maybe couldn't. And so yeah, I think our the sort of technical review guy agreed with me. I could just conclude that Katy Perry is a force.
Sarah, there's a question in the chat.
Yeah.
I was wondering if the person asking it would be willing to speak up.
Yeah, hi. So my question was, like, in your previous slide, you were showing when we have more than one ion, and you were showing that how we can couple them. So I was wondering if there are Coulomb forces, how do we take that into account, and does it interfere with what we are trying to do with them?
Totally, yeah. So like the Coulomb forces are actually really awesome for ions, because you kind of like, in order to get this kind of entanglement, in order to do a gate where, you're trying to get these two qubits, like the output that you get has to depend on both the inputs you give it. So obviously, like, these qubits, they got to talk to each other somehow. And so the Coulomb force is actually like how the two ions like talk to each other. And yeah, it'd be kind of trickier for us to do gates if we didn't have the Coulomb force. That's one nice thing about ions, I think, is that they interact with each other pretty strongly. Does that make sense? Or?
Thank you.
Yeah.
And
and it's also
question.
pretty awesome. One thing is like,
no.
Yeah, you can like actually like if you're doing gates on your ytterbium, and then we'll actually have like barium, like outside the ytterbium or whatever, just hanging out, and we can like laser cool the barium on the outside, and because they're coupled through the Coulomb force, we can actually like cool down the ytterbium without having to sort of interrupt their bits. They because these bits are sort of different electronic states of the sorry, my slide is not advancing, but anyway, yeah, the bits are different electronic states of the ions, and so yeah, with the Coulomb force, it's just really convenient for a number of things. Here we go.
And Sarah, so do you also put barium? You also load barium?
We also load barium, actually. Yeah, we don't do any of the gates on them, but we like just do sympathetic cooling of the. So we like, yeah, we basically through the Coulomb force, when the ytterbium wiggles around, you can then transfer that energy over to the barium. Like if you ever see like, you have two pendulums, or like, and you you start one swinging, you can like get all the motion over to the other pendulum. That's kind of what it's like with ytterbium and barium. You put all the motion over in barium, and then you can just like remove it from barium without having to talk to ytterbium to get things to be cold.
And there's another question in the chat. Does the person want to? People, unmute yourselves. Does the person want to? Okay, so the question is, are there chances that the laser impacts another qubit than the one that you want to address?
Yeah, totally. Yeah, we have to worry about all that kind of like all these sort of imperfections and whatnot. And so I think like the specific details of how we do the gate, we try to make that robust to imperfections, and then we might have to like play some tricks, but like totally. Sometimes, let's see, I don't know if I can go way back, but we have all these different like gate zones, all these different places where we're doing the gates, and like sometimes we want to do a gate on this one, on these two qubits, and we don't want like the laser light to randomly scatter over to like some neighbor that we didn't want to be talking to and stuff like that. So yeah, we have to worry about all that. That's a good question. Cool. Is that it? Sweet. So yeah, this is basically, take that, we do that, we do some more operations, and then we measure. And so speaking of robustness against errors, the kind of gate that we do can be sort of called a quote unquote geometric phase gate. And I'll tell you what that means. And that in some sense can be robust against errors. So you can think of like, yeah, all the bad things that can happen, and kind of design a protocol so that you're not sensitive to the bad things that can happen. So yeah, like if left shark's going around like this path and it's like flat, for example, he goes around in a circle, comes back, and it's basically where he started. But sort of intuitive picture of geometric phase, if you're pointing this direction and you do the same thing, but you're on a sphere, he's just like always pointing this direction. He's always traversing like sort of this way without changing which direction he's looking. You can go around in a closed circle or closed loop. You end up back where you started. You didn't rotate your orientation, yet you return and you're pointing in a different direction. That's kind of just like an interesting thing to me. I think it's cool. And the nice thing about doing that, so say I'm trying to like rotate which way I'm pointing, I'm trying to, change my phase. Yeah, if say, I tend to wander or whatever, and that's just something that I'm gonna do. If you design your gate this way, basically you can take this different path, and you still end up changing your rotation by the same amount. It ends up only really depending on like how much of this angle you enclose with your path. So it's just like there's always like certain kind of things that we can't control very well. And so I think designing a protocol that's insensitive to those things is always helpful. Yeah, so we put the ions together, we do our gate, and then we re-separate them, and then they can be transported to go talk to different ions. So yeah, in our computer, might look something like this. So we load our ions up here. We can do a what we call a 1 qubit gate, which is we just change one of the bits kind of independently. We can do that to both ions in parallel. And then to get the two ions to talk to each other, we put them together. We put our lasers on to do our 2 qubit gate. So that's like, the Katy Perry of left and right shark. And then we can do a swap. So if we want to, so remember up here, like the green ion was on the right, but we can just switch. We can use our electrodes to switch the left and right ions. And then we can move that qubit over there so it can interact with this guy. And then at the end, we do all of our, this like circuit, all these wires, whatever. I find them confusing. We do all our stuff, whatever. And then like, we finish our computation, and then we have to go look at what the answer is. And then so we measure. And so in real life, this is a camera taking a movie of what's actually happening. So you can see, let's see. Yeah, this ion, I think it starts here and then it flies over here, gets loaded. Yeah, there we go. Gets loaded, goes over there. Now they're next to each other. And then you merge them so they're in the same little like kind of, I like to think of like the where they live in their potential well. It's just sort of like sitting in a little egg carton or something. They're in the same like spot in an egg carton. And then they can interact. You turn on your gate lasers. Do your gate, and then you can re-separate them. And yeah, here's a video of us swapping 2 ions. This is like actual pictures. The ions, they're emitting. You can basically like light them up with the lasers, so they're emitting photons, similar to like say you have a sodium lamp on the street or whatever. It's that orange color. That's that's an atomic transition, and you're just kind of like repeatedly giving, exciting the atom, and then the atom is like releasing those photons from wherever it is. So that's what we're looking at on our cameras, swapping the ions. And so yeah, we can do some stuff in parallel. I think the challenge is always, you know, we're gonna want to add more qubits, and you know, in any, you know, computer architecture, I guess, like, you don't want you know, the computation to take like exponentially longer when you add more qubits. So like with all these different zones, we can shine the lasers on in parallel and do 2 qubit gates, yeah, totally in parallel. Then we can move them around and then you know, connect them differently and do some other 2 qubit gates. And so in the lab, there's all these different components. So I don't know if like people are all physics majors, or if like, you know, there's some software engineers, electrical engineers, whatever. But there's all kinds of engineers, I guess, that all come together to make it work. And so, you know, if you're building up a lab and you start with the mechanical engineers or whatever, you have to make all the structures that, you know, hold all the pieces of hardware. You know, the ion sitting in a trap, the whole thing's in this ultra high vacuum. I think it's like a somewhat better vacuum than whatever the vacuum is on the moon. It's which is a few orders of magnitude better than the vacuum in like sort of where the satellites are orbiting, because we just can't have any background, like, you know, we're breathing air, that's like molecules and stuff. We can't have any background gases coming in and hitting our ions when we're trying to do our computation. So we have to prepare this where kind of like we have to first like suck out all the background stuff, and we continually sort of be like sucking that out. We do everything with liquid helium, so we have all this like cryogenic stuff. Like our trap itself is at like, I don't know, 30 Kelvin or something, which is pretty cold. So yeah, all this like mechanical supports, etc. We work with mechanical engineers to do that. We also have dedicated optical engineers. So they both work on the laser sources that we use to talk to the ions, and then all the optics, so all the lenses and mirrors and stuff. It's kind of like a microscope in reverse. We have all these kind of big laser beams, and we focus them to be, you know, just right, so they can talk to the tiny little spots on the ions. So they set all that up. They help us with the measurement optics and stuff. And then when you run the computer with all the electrodes, you want to, you know, switch your ions, you want to move stuff around, etc. We're changing the electrodes, the DC voltages on the electrodes. Then also we have the radio frequency, which also helps confine the ions. We also have like, you know, magnetic field stuff. All of our experimental control is also, you know, done with FPGAs, etc., and like frequency synthesizers. And so we have a really awesome team of electrical engineers that we get to work with, and they, you know, design a lot of in-house electronics, because we really, like, on the market, like for other, you know, some of the stuff we need to do, you really can't buy, so we have to, you know, develop it ourselves. And finally, yeah, the software engineers kind of like put it all together, so help our computer talk to our control electronics, which talk to, you know, all the hardware stuff. And they also, you know, connect our whole system up to the cloud. So it's a cloud-based service where customers interact with like a nice, pleasing interface, kind of like, you know, AWS or whatever, like cloud-based computing platforms you can do. Same thing for a quantum computer. They talk to some cloud service, and then the cloud service talks to all our control electronics, which then go and, you know, flip the bits for us, etc. So yeah, we have a really, really awesome team of software engineers and like IT as well to deal with all that networking, and they make a compiler and etc., do all this computer science stuff. And so to scale this, right, like, you know, we like quantum computers generally right now are just starting to have sort of an interesting number of qubits, where maybe you start to think about doing stuff that a classical computer couldn't. But to continue, and like I would really love to do some interesting chemistry simulations, etc. There's a lot of things you could do though. We're gonna need to continue to scale. And so the path we envision is go from this linear trap to a two-dimensional trap, because you can like sort of connect stuff better. You know, when you like this one, you just have to keep it, making it longer and longer and longer. And you know, if it's 2D, there's different ways you can get things to connect. And then finally, maybe sort of modular chips connected by integrated photonics. So this would be like, you know, instead of having the lasers have to bounce off mirrors and go through lenses and stuff before it goes into, you know, before it goes into our vacuum chamber, it would all be part of this sort of microfabricated chip, just like how a normal computer, everything's on your chip. And so, yeah, that's the end of the science discussion. Maybe I should stop for a minute and see if there's any questions about that.
Yeah, that's super interesting. Hey, this is Rob. You mentioned two questions. One is on the last slide, you had something about magnetic conditioning or something like that. 2 slides ago, sorry. Yeah, what is? Yeah. Can you say a little more about what that is?
Yeah, that's a good question. My corporate overlords gave me this slide, but no, just kidding. But probably just like we have some magnetic field to give the ions, to make sure that the ions have a particular direction that they're oriented to, because the ions they kind of have, yeah, they have this thing called spin, which that's exactly the thing that like Feynman said he didn't understand well enough to explain to people. But anyway, so you know, you think of it as like it kind of like the electrons going around the atom, right? And has like angular momentum. I don't know if you're a freshman or not. Sorry, but I'll just answer for everybody. So yeah, the electrons sort of like going around the nucleus. It has angular momentum, and you know, like a gyroscope or whatever, it's got some direction that it points. And so yeah, the magnetic field's sort of the direction, I think, is relevant, because that can control actually what states of the ions we talk to. And you know, we need to make sure we're only talking to the 0 and the 1, or like, you know, the states that we want to use for whatever we're doing. And then also the magnetic field can also change the energies of all the different things we're trying to talk to. So that needs to be kind of stable as well.
Cool. If I could steal one more question.
Yeah.
So that you use like RF fields for traps, and I know there are different ways people, sometimes they use static, like magnetic fields with some electrostatics. There are a couple of different ways that people track particles. Can you talk a little bit about, you know, what's cool about the RF kind of energy well versus other ways? There are probably some trade-offs.
Yeah, I guess so. I think you need like some kind of time varying field in order to trap an ion without, like, I mean, I guess one way to maybe trap an ion would be like, oh, you could have some like charged sphere all around the ion that would like keep it in the middle. But if you don't want to have any like stuff, like physical stuff with charge, like basically where the ions are or whatever, and you need to confine them, I think you need like a time varying field, just because of like Maxwell's equations or whatever. And so we have like it's a surface Paul trap is the particular kind of trap we use. And so yeah, going back to what Feynman said, let's see if I can explain this. So the the RF is kind of changing up and down. I'd be nice to have a chalkboard in PowerPoint, but you could think of it like it's like that egg carton that the ions sit in. Oh god, this animations. There we go. Yeah, this like egg carton here. It's kind of a misnomer. It's actually like this egg carton thing is like flipping. So like right now, you know, it looks like it's at the bottom of the hill, but like as the RF's changing, it turns from being at the bottom of the hill to being at the top of the hill, etc. And so like one like sort of hand wavy picture is that like, the ion is kind of like moving at a particular frequency, and it just so happens that it matches up really nicely with the frequency of the how the trap's changing, so that like every time it ends up out here, on average, it wants to roll down the hill, and then every time it ends up here, it wants to roll down the hill. And so even though like maybe on average when it's in the middle, it's kind of at the top of the hill, it doesn't really care, because by the time it gets out there, like the potential has flipped again. I don't know if that made sense, but I tried.
No, that did. Cool. Thank you.
Yeah. Cool. Yeah. So yeah, second part. I'll just talk about. Yep.
I have a question.
Totally.
Just so the pictures that you showed of the ions, those are like pictures of like basically a single atom, right?
Yeah.
But the atom is like way smaller than that. So
yeah, you're right. Yeah, so like why it looks like not, you know, 5 angstroms or whatever.
No. It's just that I sometimes get this question.
Half an angstrom.
Like, all I'm saying is that like those are super impressive because you're seeing there like images of a single ion, of a single atom, but atoms are way smaller than the blob that you're seeing there.
Yeah, no, totally. Yeah, this is actually my first time seeing individual quantum particles as well as when I started working at Honeywell. I used to work with like a lot of atoms all together, and it wasn't just like, you know, one thing. But yeah, so you know, we can hold the single ion, and then you know, it's just like scattering, it's emitting photons. So it's like we don't really need to see be able to have like a microscope so we can see where the atom is. But we just need to like basically like our microscope just needs to be able to see that like, oh, this atom's here and this other atom is over here. And it's kind of blurry because we can't you know, like the resolution of our microscope isn't very, you know, isn't good enough to see something as small as an atom. But it's this little point. You can think of it as a little point that's emitting light, and then you can kind of, you know, our resolution blurs it out, but you can still see the point.
And do people do like super resolution imaging of ions? Would you gain anything?
Yeah, I don't think so, because I think our super resolution, like, usually, I think it usually takes a long time, kind of. Well, there's always like trade-offs, right? But like we're not really limited by our resolution, because our resolution just needs to be good enough so that when we measure, we're measuring like the photons from only like the left ion or the right ion or whatever. So we just need to be able to distinguish between that. So like the resolution that we need sort of depends more on you know, like how our trap, like the dimensions of our trap and like the spacing between the ions in the trap. And there's not really reason to go to finer resolution because we already know sort of that there's only one ion there. So like you don't need to like, yeah, see down at that level. See, any more questions about the ions? Cool. Well, yeah. Now I'll talk about yeah, my career path. So, you know, you guys are freshmen. I'll talk about my early undergraduate work. I started off in an electrical engineering lab, just soldering, basically, just putting together circuits. I never really understood what the circuits did, but like didn't really matter. Like the grad student I worked with just needed a bunch of stuff soldered up. And it was a good place to get started. Like I learned some stuff, like kind of understood at some basic level how things worked. Yeah, it was good to just jump in, get used to working with your hands, et cetera. Super fun. And like it was a good way to get access, I thought, to mentors too. So you could like always ask people who are farther along than you are for advice. And then I was like, okay, I'm a physicist. I'm going to work in a particle physics lab because I want to understand the universe. And like, I wasn't very good at it. I just think it was like kind of like not the right fit for me. I didn't really make any progress. I probably didn't show up to work as often as I should have. And like, whatever, like it just wasn't the right fit. So like, yeah, I just hopped around until something stuck. Then I did an RU, so it's a research experience for undergrads, like super fun. Yeah, they'll like pay you to go to summer camp. I mean, it kind of felt like summer camp, you know. It's like we lived in a house with like 20 people. It was like some frat house at Stanford, and yeah, I worked at Slack, and yeah, that went a little better. I think I actually did science, but that was I already finished 2 years of college before I felt like I was like, oh, maybe I did a little bit of science. But you know, those 2 years working in labs before were still like really informative. Like I got better at using a screwdriver, etc. You know, and then after that, I super failed my quantum mechanics midterm. I got like a 29% or whatever. Just like, so you know, you can fail some midterms, fine. Like, you know, they'll still invite you to give a talk at UCLA or whatever. Yeah. So anyway, I think I didn't sleep the night before, so I would tell my freshman self, like just sleep 8 hours a night, like you can do it. Like, I don't know. So yeah, I don't know. I kind of flailed around for a while before I found a lab that really was awesome for me. And so yeah, I started working in ultra cold quantum gases. So by ultra cold, I mean, yeah, we mean like 10 nanokelvin or something like this. So like however many orders of magnitude colder than room temperature, like 11, 12 orders of magnitude. But like that, I mean, that's not very, it's not like you're gonna, I don't know, get frostbite from them. Like by ultra cold, just kind of mean like, you know, temperature is sort of like how much the atoms are like jiggling and wiggling around. And so by ultra cold, we just mean we've like removed all the motion. And so we're really kind of controlling the quantum states of these atoms. But you can see, yeah, it's not like little dots like the ions were. It's like a big cloud of a lot of atoms. And yeah, you can do some really interesting, it's called more like quantum simulation. So you make these atoms behave like, say, electrons in a superconductor would behave. And so that's what we have, these like vortices, just sort of something that happens, yeah, in a superconductor when you, you know, try to change how the electrons are like rotating. And so, yeah, that's pretty cool. I really liked it. It was just like, there's tons of, you know, it's vacuum stuff. I got to, maybe I should have been an auto mechanic. I don't know. Like I had to, you know, it's fun to use wrenches and like put stuff together, and like we had these fun tabletop experiments, whatever. So like, yeah, different places you can go from there. I mean, there's Caroline. Caroline and I work at Honeywell now. We both did our PhDs in fairly similar fields. There's Jacob, though. He's an undergrad. He just joined the circus. He's a professional juggler. He's like, okay, I'll go to MIT, but like, fine, mom and dad. But like, then I'm going to the circus. And like, yeah, he did. He's super successful there. Kevin Fisher did his PhD also in quantum physics, but now he's doing like AI for radiology. So, you know, there's a lot of different ways you could go. And I was chatting with Caroline because we work together now, and we thought we'd caption it as, I'm surrounded by equipment and I have no idea what any of it does. I mean, we knew I had some idea what it did, but like, you know, I don't know, it still takes me like some time to really get a handle on stuff that's like so new and so different, and like just the process of, you take classes, but then you know, understanding how to like with your hands like make your atoms you know, do what they did in your quantum mechanics class. I don't know, I found that to be a bit of a learning curve, and it was still a ways through grad school before I felt like, I don't know, I really knew what I was doing. So yeah, I finished that up. I was like, that's really fun. I finally found something I think is fun and I want to do all the time. So I decided to do it for my PhD as well. And so for my PhD, I made an atomic clock based on neutral atoms. So again, it's like a bunch of atoms, not just like these little ions that we're sort of manipulating individually. So I worked with Jun Yi, and like, you know, every time he took a promotional photo, we always like made fun of him. So like, this is my team, they were awesome. yeah, we had a lot of fun. We cooled atoms down so we could put them in a 3-dimensional crystal with exactly 1 atom per site in this crystal. So we were actually trying to get the atoms to not talk to each other because we were trying to make a really accurate clock. So it's sort of like opposite quantum computing. It's also like very similar. So, you know, the thing that ticked in our clock was a laser. It's sort of like the flywheel. You know, like lasers or whatever, light is an electromagnetic wave. So it has the crests and troughs that go by over time. And so this like kind of going up and down and up and down, that's essentially what makes our clock tick and talk. And so these crests and troughs, I mean, if you're trying to make a really good clock, you want them to be very stable. So our ticks and talks are so stable that you can shoot it to the moon and back, and it will still the waves will still align perfectly with themselves. And we based it on strontium atoms. Same deal. We had 2 different states. So it's like essentially our 0 and our 1. And so here it's a little different. We start with like 1,000 atoms, and we're not resolving like which atoms where. You hit them with a laser. It's really similar. You hit them with a laser, put them in this superposition state, and you measure. And then when you measure, your coin was like flipping in the air until you looked at it, essentially. And then we count how many atoms ended up in the different states, and that's sort of how you get the information to feedback on this laser. And then the laser kind of is your clock, and you can use that to make time measurements or whatever. So I mean, this is essentially how GPS works, et cetera. They use microwave frequencies instead of lasers, but basically something like this is happening on board all these GPS satellites, and you're measuring all these different time delays to figure out your position on the planet when if it wasn't COVID, maybe like I would use my smartphone to like go somewhere from like an airport or whatever to give this talk. But yeah, that's how that all works. And it's sort of the same thing where the phase of this superposition state will change over time. And, just like we can use that to make a computer, we can use that to make a clock. So you kind of like set your clocks together, you wait, and then you compare again to see, if someone's late relative to the other person. So yeah, with the laser, you go to the superposition state, it's kind of rotating. And then if you're late, maybe it's going to rotate a little too far before you get there. If you're early, it won't have rotated enough. And when you actually make a measurement, you can kind of think of the answer you get happen with some probability. And it's sort of given by how much of the pie you're looking at that particular time. So like the phase between your 0 state and your 1 state is gonna give you the probability that you read out one or the other. And so if you average over 1,000 atoms or whatever, how many of them are in the excited state or the 1 state versus how many of them are in the 0 state or whatnot, that's going to be sort of proportional to how this pie is rotated or a coin has flipped or what have you. And so like, what does this look like? Like, what do we do every day? We wrap things in aluminum foil. It's fun if you're into that. We have to bake out these ultra high vacuum chambers to get anything that's stuck to the walls of our chamber. We want it to kind of evaporate off, and we suck it all out before we run. You can spray things with helium. Pretty fun. You can align lasers. So yeah, these lasers are all kind of like bouncing around off all these mirrors and stuff on this table. And I'm like turning knobs on the mirrors to change where these lasers are pointing. If you're into high fashion, you can wear these cool suits. So sometimes we have to do clean room work if you're working on some of the laser stuff or some of the ion trap stuff. It's kind of gross, like your skin just like sheds off, and like that's what dust is made out of, like ew. But so we wear these Tyvek suits and like face masks, hairnets, etc. If you like making circuits, do a lot of that. And this is all really similar at Honeywell, except I would say Honeywell is like a larger scale effort, and it's more like collective, where the whole company really has a common goal. So we're always really psyched when like any team does anything like good. It just like, you know, makes our computers work better, and it's pretty great. And we also have, I would say, more, a lot more engineering support, because we're really trying to make, a commercial thing. Great. And so after that, I had to pick a postdoc, and like, quite frankly, in the last year or so of my PhD, I knew a lot of people who died, and I was just like, why am I doing quantum physics, or why am I doing clocks and like whatever? And like, so anyway, like, you know, if you ever cry in lab, like, you're not the first, for sure. I'm pretty sure everyone has cried in lab, actually, for whatever various reasons. But yeah, I thought, you know, I love measuring things, like clocks are sweet. I like lasers, but I kind of want to do something that maybe you can uncover, sort of at the molecular level, the mechanisms and treatment of disease. So I decided to get involved with, it's called like cryogenic electron microscopy. So this is where you get the real good resolution, and you can really see. I actually don't have a picture, but the pictures that we can reconstruct, you can see where every single atom is in some biological molecule, and you can kind of like, they're like, these proteins are like little machines that kind of, little motors, little different kinds of machines. Some of them like walk around, some of them, I don't know, some of them like open and close sort of gateways to various parts of your body, etc. And then the wavelength, then the size of the atom, it's like 2 picometers. And so we shine the electron beam through this sample of flash frozen proteins, and then we look at it. Except traditionally with these microscopes, you actually, most of the information that's contained in this sample, you just throw it away. Like, you're not able to image it. And so if you take the world's most intense laser and put it here in the microscope, you can actually take that information that normally you throw away, and you can actually transfer it onto the detector, which is really cool. So you use the laser to manipulate the electron beam, so you can get out like 10 times more information, and that way you're able to see things that you weren't able to see before. So that was really fun. And then I was like, do I want to be a professor? Nah, that's okay. Oh wait, sorry. Yeah, this is what it looked like. So this is when we shove stuff in the microscope, putting our laser thing in. And this is what it looked like with optics in, optics out. We have a pretty powerful laser, and then it gets kind of enhanced inside the system. So it was like, the intensity of our laser was like 40,000 times the intensity of like a laser in a laser cutter that can cut through steel. So yeah, it was fun. Then I was like, yeah, I'll try industry. You know, I think they have more formal management training, and you know, if I want to learn how to do business, or learn how to do budgeting, or learn how to manage a team or whatever, I was just intrigued by the more sort of corporate formal structure or whatever. So I decided to go to industry. And so, like, what is Honeywell? Do we just make thermostats? No, actually. So we make a lot of fairly advanced technology. There's a lot of different divisions, like aerospace, buildings, really advanced materials, microfabrication. We make, you know, N95 masks, etc. And so in the organization, Honeywell Quantum Solutions is actually sort of its own special little division that's like not under these other umbrellas. It started fairly recently. And like, why Honeywell? Like, so I mean, you know, if you ever fly in an airplane, like the sensors and whatever control electronics, a lot of those are Honeywell. If you drive a Toyota, the coolant comes from Honeywell. I have a Toyota. And so like all these different things that you need to control ions, actually, like, Honeywell has decades of experience in them. So I mean, it kind of makes sense, like a hardware company would be, you know, a good place to develop a quantum computer. And so, yeah, there's like a lot of women at, this isn't even all of them, but like at all levels, you know, we have some like managers, our chief legal counsel. We went to undergrad together. We went to grad school together. You know, senior scientists. I don't even have our chief scientist, Patty, or like my project lead, etc. This is just like some fraction of the people, but yeah, all levels of the company. And also we have a lot of different tracks you could go. So you don't, if you get promoted, you don't just get like stuck in middle management forever. You can go technical, so you can just keep like, you know, progressing your career and just stay in the lab, stay technical. You can also go into more of a management direction or a business direction. I think there's all these options. And so I think I'm running a little over time. But yeah, I would just say there's so many different career paths you can take after a PhD in quantum physics. Like this is just a random sampling of my grad school friends. Like a lot of us are at Honeywell because we like living in Colorado. But yeah, like he's in DC doing science policy. She's doing data science. She's the project manager for like balloon missions to measure atmospheric chemistry. She went into journalism. She did kind of like XUV lasers, and so now she's works for Siemens doing CT scan machines. And like a lot of people are like, I don't know, maybe a third of the people are like now postdocs, national lab staff, or professors. But like, there's a lot of different directions you can go. And like, yeah, I felt like there are a lot of options for me after. Like they totally would have let me like dissect mice and like image mice brains. That was like another thing I considered. So yeah, that's about it. I'll take some questions if there's time.
Yes, there's time. Yes, go for it. And thank you.
I have a question.
Yeah.
My name's Ashley. I actually go to Howard University here in Washington, D.C. So my question is to you. I love your background. I love how like cool you seem, because the thing is, I feel like a lot of people have a misconception is that, you know, that you have to be like a genius to be on this path. You know, ending up at Honeywell and whatnot, which is amazing. So my question to you is like, as I'm a third year PhD student and I'm like trying to figure out my way through like, you know, graduate school and figuring out like what I like, and obviously quantum computing, I do see myself doing as a full-term career. So would you say that like for someone at my level, what should I try different types of internships? Because right now I intern with the Naval Research Lab, but I'm trying to figure out if I need to do like different things to try to, because I want essentially a job in industry like how you have. Like I want to end up at either Honeywell or Google or Intel. So like, what should I do to make myself, I guess, stand out to try to get one of these jobs? Being that I don't feel like I'm a genius, but I do know kind of what I'm doing with quantum computing.
Yeah. Me personally, I just kind of did whatever was like I felt was fun and like productive. And I think when you're being productive, that can be pretty fun too. So I mean, I switched what I was doing, like kind of at least in undergrad I did, till I found something I liked, and then I kind of stuck with it. And like I don't know, I think it's nice. I really don't know. I've never sat on a hiring committee or whatever. Like other people can chime in, but you know, I like to follow through with stuff or whatever. Like I feel like PhD student, I don't know, just do a great job at your PhD or whatever, like, and like, you know, get stuff done there. I never did any internships or anything like that, but maybe it's probably different. Are you like in an engineering field? I feel like engineers do more. Yeah.
Okay, I was gonna say, because I'm a physicist, but I mean, just in case that I don't do internships, I guess what I'm trying to ask, like, even if I don't do a whole bunch of different internships, that means I still possibly have a good chance of getting a job like yours.
Yeah, totally. I never did an internship. Like since I like started my PhD, I've always been in a lab. Yeah. And like I switched to like kind of between, so I like would finish something like my PhD and then like switch for my postdoc to try something new. Then I switched back for you know, for my industry job, and like, yeah, it was all good. So I don't know, just like, yeah, I don't think anybody has to be a genius, like, or whatever. I don't even know what that really means. Like, you know, like, I was thinking about back to undergrad or back to how people were like, I guess like, yeah, a lot of people here are freshmen. Like, I don't know. I think, you know, your freshman year, you're like, how well you do, that probably depends on how much property tax money your school district growing up collected or something. Like it has nothing to do with anything, right? Like, and so like people come in, some people are like, oh, I'm so fast at math, some people aren't, and then like by the end of I know it wasn't really your question, but like there's a lot of freshmen, so I figured I'd just say it. Like I felt like by the end of the PhDs, like, you know, like, or by the end of undergrad, like it changed, like who was good and who wasn't or whatever. Like my PhD advisor would always say, like, you know, it never really matters what level you come in at. Like what matters is more your personal slope as far as improvement goes. You know, the y-intercept doesn't matter, it's the slope, is like what you would always say. And so yeah, I mean, I'm still learning stuff a bunch too, and like I think it's just like, maybe it's just a matter of like how patient you are, like how smart you come off as, or like, so you like how long are you willing to sit there and try to understand something or whatever.
Thank you.
Yeah.
If I can just mention something really briefly for Ashley and some of you others, having been down this road, I was a physics major on the experimental rather than the theoretical side. And so for me, the segue into engineering then was quite natural. And as one of my father's friends said when I was in high school, he found I was a physics major. He said, well, you had an industry, you're all engineers anyway. So there's always this pressure between what's a near-term payback that they want to invest in as R&D for a company versus what's a longer range, more fundamental research that you might do in a national lab or something. And kind of be open to both, because you really don't know where you're going to end up. Things happen and life takes surprising turns. And so be open to that as well. The other thing is network. Get to know people, attend conferences, lectures like this, seminars like this, make your contacts, LinkedIn, talk to your professors, office hours, find out who they know, what they've been doing, talk to some of your friends about what they're doing on internships, but network your brains out, because that's really going to help you find out what's out there, who's out there, and what do you want to do, and how would you fit in. I think that'll help you out a great deal as well.
Thank you. That's very true. Thank you so much for that.
So can I ask a question? I'm just wondering, throughout your path, did you have this like aha moment, being like, okay, yes, industry is what I want? Or like, how is it that in the end, like, you made your ultimate career path choice?
Yeah, I guess I like, they have all these like early career panel things for postdocs, and like every time I went to one, I like kind of like, I feel like a lot of people kind of, I don't know, expect you to be a professor. Like people think like, oh, if you can be a professor, that's the best path. But like the people who are usually giving you that advice are all like professors, or so it's like, I don't know. So every time I went to that and like talked to professor friends, I was just kind of like, is that what I want to be doing? Like, I don't know, because it's just like sort of something I assumed I would end up doing. And then like, I was kind of like, I don't know if right now that's what I want. And then like I wouldn't say like a moment, I would say like, like Stephen Moses like whispering in my ear, like, come to Honeywell, like it's great, like, or whatever. And I just I had a lot of friends at Honeywell and stuff, and like talking to them, they all seem pretty happy. And just like kind of just randomly happen. And I feel like, you can always, I feel like you can go back, right? Like Mark worked at HRL for quite a while. And I was just kind of like, maybe I'll take a little breather here for my whole career, maybe for a little bit, whatever. But I kind of like, so that there's some more like sort of formal management training maybe in industry. But then again, like, I had to have someone review all my slides. Like, I don't get to make all the, if I want to change my design, I have to go to the engineering change review board, or like, but they'll if you're right, they'll change it. If you're like, oh wait, I found a problem, like they'll obviously change it. But it's less independent. But I really like working with peers. And like, so that's just like, what I decided to do least for a while, for sure.
Thank you.
Yeah.
Are there any more questions from freshmen? Oh, actually, I see a question in the chat. Someone's asking, what kind of skills do you need to develop in order to get involved in the quantum industry?
I would say like if you can just get any, I mean, if like, especially if you're doing anything, like if you can just get a job, like a research job or like some internship or whatever, like you could just start and then develop all the skills like there on the job, like while you're being paid. I mean, I didn't really have any skills when I started. Like I would say now, like, Python programming is good, like basic op-amp circuits, not a bad idea. If you want to be fancy, sure, like go program FPGAs. I never really got that into it. But just generally like working with your hands, I think, like machine shop courses too. If there's any, if you can manage to take a machine shop course. I took one my freshman year of college. We like made little Stirling engines. It was cool. If you want to do experimental stuff anyway. I think just like any kind of like hands-on sort of experience with like power tools, etc., is fairly useful. But yeah, if you just like show up, just get a job, just like email a million professors, just keep emailing until you or whatever, until you can like find some place that will hire you. And I think just developing those skills on the job is great.
Do we have any more questions from freshmen?
What's your favorite thing about quantum?
What's my favorite? Can you say that again?
What's your favorite thing about like all this quantum?
I think like working with my hands in the lab, the tabletop kind of experiment sort of stuff. It's pretty fun.
Thank you.
Yeah.
I think there's a question in chat. What computing skills do you need?
Like none. I don't know. Like you can take there's like some online Python whatever course, like or MATLAB, or like things to write little scripts to like look at data is pretty useful. Or you might have to like have some device that you're controlling through some but like with Python and like Stack Exchange, I don't know, just develop your Googling skills. Like I just like Google stuff. I look on Stack Exchange and I like copy and paste other people's code and modify it. I would say that that's like 90% of what I do. And then it's really fun to understand computing in a more general sense, but I think you just go with what's interesting to you as well. Like if you want to go in a more theoretical direction, or like I would say, I don't know, like taking linear algebra is a good course to take, I'd say. And then I don't think you really need any computing skills per se. Like I think like if you want to do what I do, it's just like experimental physics, it's just like you'll just like Google whatever you need to figure out how to do and be fine.
I think there's a question. How did you get into like doing bio research? Like, did you need biology classes?
No, I just like, I mean, I think if you can do the laser stuff, there's a lot of opportunity in biology. I'd go back. My computer is just like struggling. Oh yeah, but like Liz, like she just did like X-ray lasers, and like then she wanted to go into medical imaging, and she just applied to the Mayo Clinic, and they just took her. They took her husband too as like just a spousal hire. He was a particle physicist. I think the particle physicists are usually like sort of better at coding than experimental atomic physicists generally. So he's doing like AI for in the radiology department. He's like a professor in the radiology department now, and his PhD was completely just in particle physics, and she works at Siemens or whatever. So yeah, I just like, you know, if you can convince people enough that like, oh, I can measure stuff with lasers or whatever. I was gonna go back to, yeah, other people who switched to biology. Seems pretty common. Even like Steve Chu, like our former Secretary of Energy, you know, got like some Nobel Prize for like laser trapping or whatever. And like he has a biology lab now or whatever. So yeah, and then here point options. Yeah, so I mean, yeah, Chang from back then, he works at Verily doing, well, he did his postdoc. I think from PhD to postdoc's a good place to switch. He did his postdoc more in like mouse brains, because you know, if you can turn lasers on and off and like, you know, blah blah blah, like they'll probably hire you or whatever. So he did his postdoc there, and now he works at Verily. Iban's now doing his postdoc in like biochemistry or whatever. So yeah, and they're like willing to hire me with like nothing. I audited like undergrad classes, like undergrad biochemistry. I audited, or like EDX is really great, edx.org, or Coursera too, for like, yeah, just like online courses to learn stuff that you don't know. But yeah.
Thank you.
Yeah.
This has been so great. Thank you, Sara.
Yeah, thanks everybody.
Is there, well, before we say goodbye, any last minute questions? All right. Well, this has been really, really awesome. Thank you so much.
Yeah, thanks
I
for the
hope
opportunity.
everyone loved the shark and Katy Perry's as much as I did. And thank you, everyone. And we'll see you next week to learn about, I don't remember what we're learning about. Oh, cool. We're going to have Donnie Pearson talk about photons and quantum computing.
Sara, you're awesome. Thank you.
Sweet. Thanks so much, everybody. Yeah, nice to meet you folks. Have a good one.
Thank you.
Thank you.
Thank you so much.
Bye.